look at what we assumed for most of human history, and I mean the serious scientific part of human history, not just the myth making part, we assumed that our solar system was a template. We have a small rocky planet close to the sun, then another small rocky planet, then another, then a slightly larger one with water on it, then a gas giant, then a bigger gas giant, then a couple of icy giants at the frozen edges. And that is how a solar system works. That is the model. That is what gravity and chemistry and 4 billion years of physics produce when a cloud of gas collapses around a medium-sized star. We were so confident in this model that when we started looking for planets around other stars, we essentially went looking for ourselves. That was a colossal mistake. And I say that not as a criticism, it was a reasonable scientific prior, an understandable extrapolation. But I say it because understanding how thoroughly and spectacularly wrong that assumption turned out to be is the whole point of what I want to talk about tonight. The universe did not read our textbooks. The universe, as it turns out, is far more inventive, far more violent, far more strange than anything we were prepared to find. And I have been in this field long enough to tell you that is not a comfortable thing to discover. It is exhilarating, yes, but it is not comfortable. I want to talk to you about planets that should not exist, not in a poetic sense, not as a figure of speech. I mean that literally. I mean planets whose existence, when first detected, caused serious scientists to go back and re-examine their instruments because the alternative, that the planet was real, seemed more implausible than a hardware malfunction. I mean, worlds so alien, so physically extreme, so geometrically improbable in their arrangements that they forced us to throw out assumptions about planetary formation that we had held for decades. Some of these worlds rain iron. Some of them are older than the galaxy in which they live should have been able to produce them. One of them, I'll get to this, orbits a dead star that should have destroyed it. And none of this is science fiction. All of it is observational data. All of it happened. Now, before I show you these impossible worlds, I need to walk you through something first. Because the discovery of extrasolar planets orbiting other stars, is one of the great intellectual pilgrimages of my lifetime, and I don't want to skip the journey. The destination is astonishing, but the journey is what will make you understand why it is astonishing. For a long time, I'm talking well into the 20th century, the question of whether other stars had planets was genuinely unanswered. Not just unanswered in the sense of we haven't found them yet, unanswered in the deeper sense of we had almost no method capable of detecting them even if they existed. Stars are phenomenally bright. Planets are phenomenally dim. The contrast ratio, the difference in brightness between, say, Jupiter and the Sun, as seen from a distance of several light years, is roughly 1 to a billion. Imagine standing in Los Angeles and trying to see a firefly hovering next to a lighthouse beam visible from New York. That is approximately the challenge. So for a long time, we argued about it theoretically. We tried to estimate the probability of planetary formation from first principles. We wrote equations and made projections, and we waited for technology to catch up to our curiosity. I remember those years. I was at Cornell in the 70s and 80s, and the question of life elsewhere in the universe was, for many of my colleagues, too speculative to be respectable. SETI, the search for extraterrestrial intelligence, was considered by some to be at the soft, even embarrassing edge of legitimate science, and the question of extrasolar planets was tangled up in that. If you talk too much about other worlds, you risked being lumped in with the people who were not doing serious science. That tension was real. I felt it. I argued against it, often loudly, but I felt it. And then in 1992, something happened that changed the entire conversation. Alexander Wolszczan, a Polish astronomer working at Arecibo, detected planets around a pulsar. Now, I need to stop here because I need to make sure you understand what a pulsar is. A pulsar is a neutron star. A neutron star is what happens when a massive star, 8 to 20 solar masses, roughly reaches the end of its life, and its core collapses so violently that protons and electrons are literally squeezed together into neutrons under pressures that no laboratory on Earth has ever come close to replicating. The result is an object roughly 20 kilometers in diameter that contains more mass than the Sunday. It is, by density, one of the most extreme objects in the known universe. A teaspoon of neutron star material weighs approximately 1 billion tons. And because angular momentum is conserved during the collapse, the same reason a figure skater spins faster when she pulls in her arms, the neutron star rotates at extraordinary speed, emitting beams of electromagnetic radiation from its magnetic poles that sweep past us like a cosmic lighthouse. That is what a pulsar is. Now, the question I want you to sit with for a moment is this: how does anything survive that? The stellar explosion that creates a neutron star is called a supernova. It is one of the most energetic events in the observable universe. A single supernova briefly outshines an entire galaxy of hundreds of billions of stars. The shock wave and radiation from such an explosion would, to put it plainly, obliterate anything in the surrounding system. And yet, Volchan's data showed 3 bodies orbiting this pulsar with masses comparable to Earth. How? How did they survive? The answer, and this is the one that makes me put my coffee down every time, is that they probably didn't, they almost certainly were not pre-existing planets that somehow endured the supernova. They were most likely born from the debris of the explosion itself. The disk of ejected material left behind after the collapse reformed, accreted, and coalesced into planets, new worlds, built from the wreckage of a dead star. Rocky bodies condense from stellar ash and orbiting a corpse that spins 30 times per second and blasts them with lethal radiation. If that doesn't strike you as strange, you are not paying attention. Those were the first confirmed extrasolar planets in history, and they were not around a sun-like star in a pleasant orbit at a comfortable distance. They were around a pulsar. We found the strangest possible example first. The universe was already telling us something, and we should have listened harder. 3 years later, in 1995, Michel Mayor and Didier Queloz, who would eventually win the Nobel Prize for this work, as they should, detected a planet around 51 Pegasi, a star very similar to our own Sunday. The planet was designated 51 Pegasi b, and it was a gas giant roughly half the mass of Jupiter. That sounded reasonable enough until you looked at its orbital period. This thing orbited its star in 4 days. 4 days. Mercury, the closest planet to our sun, a tiny airless rock that gets baked to 430 degrees Celsius, takes 88 days to complete one orbit. This gas giant, this thing half the mass of Jupiter, was completing an orbit in 4 days, which means it was orbiting at a distance of about 8 million kilometers from its star, a distance that would place it deep inside the orbit of Mercury if it were in our solar system. The temperature on its atmosphere was somewhere around 1,000 degrees Celsius. Now, here is where I need to lay some foundation, because the problem with 51 Pegasi b is not just that it was hot. The problem is that it fundamentally should not have been where it was. Gas giants do not form close to stars. They cannot. The reason is physics. Close to a young star, the temperature is too high for the light gases hydrogen, helium, the building blocks of a gas giant's bulk, to condense and accrete. For a planet to accumulate the enormous mass of a gas giant, it needs to begin forming beyond what we call the frost line, or snow line, the boundary in a protoplanetary disk beyond which water, methane, and ammonia freeze into solid grains. In our solar system, that line sits somewhere around 5 astronomical units from the sun, roughly where Jupiter orbits. This is not a coincidence. Jupiter is where it is because that is where the physics of formation allowed it to accumulate enough material to become what it is. A gas giant 4 days from its star is like finding a glacier in the middle of the Sahara. Not metaphorically. Physically, it tells you that either everything we think we know about planetary formation is wrong, or that the planet moved. And moving is the answer: planetary migration. driven by interactions with the gas disk of the young solar system, can cause a massive planet to lose angular momentum and spiral inward toward the star. This was theoretically known before Mayer and Queloz made their discovery, but it was considered an edge case, a mathematical possibility, not something we expected to actually see. The universe had other ideas. We now know that hot Jupiters, as they are called, are not rare anomalies. They exist around roughly 1% of sun-like stars that we survey. 1% sounds small until you multiply it by the 400 billion stars in the Milky Way. There are potentially 4 billion hot Jupiters in our galaxy alone. 4 billion gas giants orbiting close to their stars, with surface temperatures that would vaporize steel, being slowly eroded by stellar radiation, some of them losing their atmospheres at a rate of millions of tons per second. Worlds that are so close to their stars that they are gravitationally locked, the same face always pointing toward the star forever, the day side an inferno, and the night side cold enough, in some cases, to precipitate clouds made of silicate particles, clouds of liquid rock. That is what weather looks like on those worlds. But here is where it gets genuinely strange. And I mean, this is where the data starts making physicists argue at conferences in ways that are entertaining to watch. Consider WASP 76b. This is a hot Jupiter orbiting its star in about 43 hours. The day side of this planet, the side that permanently faces its star, reaches temperatures of around 2,400 degrees Celsius. At that temperature, iron doesn't just melt, it vaporizes. The iron atoms lift off the surface and enter the atmosphere as a gas. Then, as the iron-laden atmosphere circulates toward the night side, because yes, there are violent winds moving from day side to night side at speeds exceeding 17,000 kilometers per hour, the temperature drops enough that the iron condenses back out. It precipitates. It rains. On WASP 76b, it rains iron. I have said that sentence out loud at many conferences, and I still have to pause afterward because the mind does not quite believe it, even when the math supports it entirely. The spectroscopic signature of iron in the atmosphere was detected in 2020 by the Espresso spectrograph on the Very Large Telescope in Chile. It's real data. It's verified. Iron rain is not a hypothesis. It is an observation. Now, I want to take a step back and tell you something about my own intellectual journey with these discoveries, because I think the personal history matters. I spent a great deal of the 1970s working on the atmosphere of Venus. At the time, Venus was considered a failure of a planet, a world that had started with conditions broadly similar to Earth's, perhaps with liquid water oceans in its early history, and had undergone a catastrophic runaway greenhouse effect that turned it into the hell it is today. 460 degrees Celsius at the surface, a pressure 90 times that of Earth's atmosphere, and clouds of sulfuric acid. I was involved in some of the early modeling of the Venusian greenhouse, and I'll tell you that when we first published those numbers, the surface temperature, the runaway feedback mechanism, a lot of people thought we were wrong. 460 degrees felt impossible. Mercury, much closer to the sun, only reaches 430 degrees at its hottest. Venus was supposed to be cooler, but Venus has that thick CO2 atmosphere trapping heat, and the physics is the physics. The Soviets landed probes on the surface of Venus, the Venera missions, and confirmed the temperatures and pressures. We were right. What that experience taught me, what working on Venus specifically taught me, is that planetary atmospheres are not merely decorative features. They are the defining characteristic of a world. They determine surface conditions. They mediate between the star's energy input and the planet's energy output. And they can transform a world from an oasis into an oven. Or, as we now know from studying hot Jupiters, into an iron forge. The lesson of Venus is that atmosphere is everything. And the lesson of the exoplanet surveys is that atmospheres come in varieties we had simply not imagined. Consider HD 1897333b. This is a hot Jupiter whose atmosphere was characterized in extraordinary detail by the Hubble Space Telescope. It has winds of about 8,000 kilometers per hour, roughly 7 times the speed of sound on Earth. Its atmosphere contains silicate particles, essentially, sand, glass. Those particles, swept along by the ferocious winds, produce something that can only be described with scientific precision as a glass sideways rainstorm. The color of this world, as inferred from its albedo, the way it reflects light, is a deep, vivid blue, not because it has oceans, because the silicate haze scatters blue light. From a distance, it would look like a sapphire. Up close, it would shred you. I don't tell you this for drama. I tell you this because this world is 44 light years away. It has been intensely studied for over 15 years, and we know these things about it with genuine scientific confidence. We are doing atmospheric characterization of worlds 44 light years away. We are doing it routinely. The sophistication of what we can now extract from a transit spectrum, the light of a star filtered through a planet's atmosphere as it crosses our line of sight, would have been inconceivable to me as a young researcher. And what that sophistication has revealed is a zoo of atmospheric chemistries, temperatures, and dynamics that make our own solar system look like a very sheltered corner of a much wilder universe. Now I want to talk about a category of planet that gets less publicity than the hot Jupiters, but that I think is philosophically more interesting. These are the super-Earths, the rocky or possibly rocky worlds with masses between 1 and 10 times Earth's mass, for which we have no example in our own solar system. And their existence raises a question I find genuinely troubling in the best possible way. Our solar system has terrestrial planets up to about 1 Earth mass, and then a gap, and then ice giants, Uranus and Neptune, at about 15 and 17 Earth masses. Super Earths occupy the middle ground. They're too massive to be conventional rocky planets, but too small to be gas giants. And the question of what they actually are, their internal composition, their surface conditions, whether they have atmospheres and of what kind, is one of the most active and contested areas in planetary science right now. GJ 1214b is a canonical example. It was discovered in 2009. It has a mass about 6 times Earth's, and its density, calculated from the combination of its transit depth and radial velocity signature, is too low to be a pure rock planet. It has to have a substantial fraction of lighter material. Water is the leading candidate. Not liquid water at the surface, necessarily at the temperatures and pressures involved. The water would exist in exotic high-pressure phases. What physicists call Ice 7 and Ice X, forms of ice that are not cold at all, but are instead incredibly dense crystalline structures formed under extreme pressure. Beneath that exotic ice layer might be a rock core. Above it, a steam atmosphere. This is not Earth. This is not Mars. This is something genuinely new, a water world with a physics of its own. But here is the uncomfortable truth I have to give you, because I said at the outset that I would not hand you easy comfort. We don't actually know with certainty what GJ 1214b is made of. We have strong inferences, we have constrained possibilities, we have ruled out several scenarios. But the internal structure of a planet 6 times Earth's mass, 40 light years away, is not something we can peer into directly. We are working from density, from transmission spectroscopy, from models of how matter behaves under conditions that do not exist anywhere on Earth's surface. The uncertainty is real, and the uncertainty matters, because the difference between a high-pressure water world and a world with a thick hydrogen-helium envelope over a rocky core is the difference between, potentially, a world that might be relevant to the question of life and a world that is not. Those questions are not yet answered. I want to stay on that uncertainty for a moment, because I think there is a temptation, and I see this in popular accounts of exoplanet science all the time, to present these discoveries as finished knowledge. Planet found, properties known, next planet. That is not how it works. These discoveries are the beginning of an investigation, not the conclusion. When we say we have detected water vapor in the atmosphere of a planet in the habitable zone of its star, that is a remarkable achievement. It is also one data point in a much larger question that we are nowhere near resolving. The humility required to sit with that, to say, this is extraordinary, but it is not yet an answer, is the same humility that science requires everywhere, but somehow feels especially urgent when the question is, might there be life on that world? Now, I promised you a truly impossible planet, and here it is. PSR B162026b. That is not a poetic name, I grant you, but what it represents has earned a nickname, the Methuselah planet. It orbits a binary system consisting of a pulsar and a white dwarf, two stellar remnants, two dead stars, in a globular cluster called M4, about 5,600 light years away. Its mass is approximately 2.5 times Jupiter's, and its age, inferred from the age of the stellar system in which it lives, is approximately 12.7 billion years. The universe itself is 13.8 billion years old. This planet has existed for 12.7 billion years. Consider what that means. This planet was already ancient when our sun ignited. It was already more than 5 billion years old when Earth formed. When the first single-celled organisms appeared in Earth's oceans, this planet had been in existence for almost 11 billion years. It predates the formation of most of the heavy elements in the universe. Elements like carbon, oxygen, nitrogen, the building blocks of chemistry as we know it, because those elements had barely been synthesized yet when this planet accreted. It formed from an incredibly metal-poor cloud of gas in the early universe, when the cosmos had barely begun its long project of enriching itself through stellar nucleosynthesis. And yet it is there, still there. A 2.5 Jupiter mass body orbiting two dead stars in a globular cluster, in conditions utterly unlike anything in our region of the galaxy, having survived the death of its original parent star, the supernova that created the pulsar, the gravitational dynamics of a densely packed star cluster, and 12.7 billion years of cosmic vicissitudes. When I think about this planet, I think about what it has witnessed. In a purely abstract, non-anthropomorphizing sense, this object has been present for the entire history of complex stellar evolution in our galaxy. It was there before our sun was a thought. It has no notion of us. It is a gas giant. It doesn't have notions, but we have an obligation, I think, to notice it, to take it seriously. And because a planet that old, in a globular cluster, challenges our assumptions about where planets can form and where life might have had the most time to develop. Globular clusters were long considered unlikely environments for habitable planets because they were thought to be too metal poor, too lacking in the heavy elements needed for rocky planet formation. But here is a planet in a globular cluster, 12.7 billion years old. It is at least asking the question out loud. I want to talk about what these strange worlds collectively tell us about planetary formation theory, because this is where the science becomes not just descriptively wild, but structurally important. The standard model of planet formation, what is called the core accretion model, says that planets grow from small grains of dust and ice that collide and stick together, slowly building up into larger and larger bodies, planetesimals, protoplanets, and eventually full planets in a rotating disk of material around a young star. This model works extraordinarily well for explaining our own solar system, Jupiter's location, Saturn's composition, the presence of the asteroid belt between Mars and Jupiter, the orbital dynamics of the outer planets. All of this falls out naturally from core accretion combined with models of the early solar system's dynamical evolution. But core accretion is under serious pressure from the exoplanet data. Hot Jupiters, as I said, require migration. They couldn't have formed where they are. Super Earths in tight orbits around their stars are so common they appear to be the most abundant type of planet in the galaxy, and yet our solar system has none. The absence of a super Earth between Earth and Jupiter is not predicted by the standard model. It may, in fact, be the result of an unusual, early, dynamical history in which Jupiter's inward then outward migration, the so-called grand tack hypothesis, cleared the inner solar system more thoroughly than is typical. If that is right, then our solar system is not a template. It is an outlier. It is strange. The universe's typical planetary system, insofar as such a thing exists, is not what we see around our own Sunday. That realization, which has been building for the past 20 years and is now, I think, unavoidable, has profound implications, not just for planetary science, but for astrobiology. For decades, when we searched for potentially habitable worlds, we searched for systems that looked like ours, a small rocky planet in a temperate orbit around a sun-like star, Earth as the template, our solar system as the norm. But if our solar system is the exception rather than the rule, then life, if it exists elsewhere, most likely doesn't exist in conditions that look much like our own. It exists, if it exists, on a super Earth in a tight orbit, or on a tidally locked world where one side burns and the other freezes and the only habitable zone is a narrow ring around the terminator, or around a red dwarf star that flares violently and periodically bathes its planets in ultraviolet radiation, or perhaps on a rogue planet, a world with no star at all. Let me tell you about rogue planets, because they represent perhaps the most radical departure from our intuitions about what a planet is supposed to be. Planets, in our experience, orbit stars. That is what a planet does. It orbits a star. That is essentially the definition, or was for a very long time, the idea of a planet with no star, a world untethered, wandering through interstellar space in total darkness, sounds like a description of an uninhabitable void. And yet we now have strong evidence that such objects exist in substantial numbers. How many? The honest answer is that we don't know with great precision, but estimates based on gravitational microlensing surveys, a technique that detects mass by the gravitational bending of light from background stars, suggest that rogue planets may outnumber stars in the galaxy. Some estimates put the count at several per star. That could mean trillions of free-floating planetary mass objects in the Milky Way alone. How does a planet go rogue? The dynamics of young solar systems are violent. Multiple planets can interact gravitationally, and in those interactions there are winners and losers. Jupiter may have ejected numerous bodies from our solar system in its early history. The grand simulations of young planetary systems regularly produce ejections. Planets kicked onto hyperbolic trajectories by close encounters with more massive siblings, flung out of the system entirely to wander the galaxy alone. It is also possible to form planetary mass objects directly from the collapse of gas clouds in a process similar to star formation, producing objects that never belonged to any star in the first place. These rogue worlds are not merely curiosities. Here is the thing that stops me cold when I think about it carefully. A sufficiently massive rogue planet 1, say 10 times Earth's mass, with a thick, hydrogen-rich atmosphere, might retain enough internal heat from its formation, from the long decay of radioactive elements in its interior, to keep a subsurface ocean liquid for billions of years, in total darkness, with no star, in the depths of interstellar space. I am not telling you there is life on rogue planets. I am not saying that. What I am saying is that the assumption that liquid water requires proximity to a star is not as secure as we once thought. Europa, Jupiter's moon, has a liquid ocean under its ice shell, maintained not by solar energy but by tidal heating from Jupiter's gravitational influence. Enceladus, Saturn's moon, is spraying liquid water into space from geysers driven by tidal energy. In our own solar system, liquid water exists far outside the traditional habitable zone. On a rogue planet with the right mass and the right composition and enough internal radioactivity, liquid water might persist for geologic timescales. And if liquid water can persist for geologic timescales, then chemistry happens. Whether the right chemistry for life happens, that I cannot tell you. But the universe is very large, and it has had a very long time, and it does not seem to care much about our intuitions regarding what constitutes a suitable environment. Now, I want to end this part of the argument with something that has been keeping me restless, something that doesn't have a clean answer yet. And that, I think, represents the genuinely open frontier of this field. We have found in the past several years a class of world described as Haitian planets, hypothetical worlds with deep global oceans of liquid water under hydrogen-rich atmospheres, potentially massive enough to maintain high surface pressures that keep the water liquid over a wide range of temperatures. K2-18b is the candidate that has received the most attention. It is roughly 8.5 times Earth's mass. It orbits a red dwarf star in what we calculate to be the habitable zone, and its atmosphere, analyzed by the James Webb Space Telescope, shows signs of carbon dioxide, methane, and possibly dimethyl sulfide. Dimethyl sulfide is notable because on Earth it is produced almost exclusively by marine phytoplankton. It is a biological signature, a biosignature. I have to be careful here. I have been in this field long enough to watch people get burned by premature excitement. The detection of dimethyl sulfide in K2-18b's atmosphere is tentative. The signal-to-noise ratio is modest. Abiotic mechanisms for producing dimethyl sulfide without biology have not been entirely ruled out. And the interpretation of spectra from planets 80 light years away involves a thicket of modeling assumptions, instrument calibrations, and systematic uncertainties that serious planetary scientists argue about vigorously and at length. I don't think we have detected life on K2-18b. I am not confident we haven't. I think we are at the very beginning of having the tools that could, in principle, detect life on a world 80 light years away. And that alone is one of the most consequential developments in the history of science. Not the answer. The capability of approaching the question, that is where we are. And here is what unsettles me most, not in a despairing way, but in the way that physics keeps me honest. Every strange planet I have described to you tonight, the pulsar worlds, the iron rain giants, the ancient wanderers, the hypothetical ocean worlds, every single one of them represents a failure of our prior expectations. We thought we knew the range of possibilities. We had our models, our theories, our solar system as a reference point, and the universe, planet by planet, observation by observation, has demonstrated that our reference point is not the center of anything. It is one data point, one planet type in a vast catalog that is still being written. Copernicus removed the Earth from the center of the solar system. That was hard for people. It took time. Subsequent centuries of astronomy removed our solar system from the center of the galaxy and our galaxy from the center of the universe. What I think the exoplanet surveys are in the process of doing, and we are nowhere near done, is removing our solar system from the center of the distribution of planetary systems. We are not typical. We are not the template. We are, in fact, increasingly looking like an unusual configuration, a gas giant free inner solar system, a Jupiter at the right distance to shield the inner planets from comet bombardment, a moon large enough to stabilize our axial tilt, a system that has been relatively dynamically quiet for the last several billion years. These are not guaranteed features of any solar system. They may be rare, and their rarity may matter not just for us, but for the question of whether intelligence arises often in the universe or almost never. I want to be precise about what I mean when I say that question is still open, because I don't want you to walk away thinking I'm gesturing at something vague. The Drake equation, which Frank Drake and I and others have discussed and argued over since the early 1960s, since that first meeting at Green Bank, West Virginia, where we sat in a room and tried to estimate the number of communicating civilizations in the galaxy. The Drake equation includes a term for the fraction of planetary systems that include a habitable world. For decades, that term was almost entirely unconstrained. We didn't know if planetary systems were common or rare, let alone habitable ones. Now we know that planetary systems are extraordinarily common. Essentially, every star has them, and the galaxy contains tens of billions of potentially rocky planets in the habitable zones of their stars. That one term, that one factor, has gone from nearly unconstrained to strongly positive in the space of about 30 years. That is a dramatic shift in what the equation tells us. But the equation also includes terms for the fraction of habitable worlds on which life actually arises, the fraction of life-bearing worlds that develop intelligence, the fraction that develop technology, and the longevity of technological civilizations. And those terms remain what they have always been, almost entirely unknown. We have discovered a staggering diversity of planetary environments. We have learned that the universe is not at all selective about the kinds of worlds it makes. But we have not learned whether any of those worlds carry life, not with certainty, not yet. And this is where I have to tell you something about the strange planets and what they mean for that question. The strange planets, the iron rain worlds, the glass sideways worlds, the water giants, the pulsar worlds, they are not candidates for life as we know it. They are something else. They are proof of concept for the universe's inventiveness. They are evidence that if we are looking for life, we need to look everywhere, and we need to be very careful about assuming that life, if it exists, will have chosen to arise in conditions we would recognize as comfortable. Earth life is adapted to Earth. That is a tautology. Life that arose on a super Earth with 10 times the gravity, or on a tidally locked world where only the terminator is temperate, or in a subsurface ocean under 100 kilometers of exotic ice on a rogue planet in interstellar space, if it exists. It knows nothing about us and nothing about what we would consider habitable. The cosmos is not organized around our survival. It is not hostile to us. Either it is indifferent, which is both more frightening and more interesting. The strange planets are the universe's reminder that the local conditions in which we arose do not define the space of possible conditions. They extend that space dramatically, violently, magnificently beyond what we imagined. I have spent 60 years being surprised by planets, by Venus, which should have been temperate and is not, by the moons of the outer solar system, which should have been inert and are actively geological, by the exoplanets, which should have looked like our solar system and do not. I have been surprised again and again, and every surprise has pushed me further from comfortable answers and closer to better questions. That is the correct direction of travel. So here is what I leave you with, and it is not a comfortable thought, and I am not going to apologize for that. We live on a planet that, by the standards of the galaxy, may be remarkable, not because we are special in some mystical sense, but because the dynamical history that produced our world, our moon, our quiet outer solar system, our stable climate over geological time, that history may not repeat very often. We are here because a very long and specific chain of events unfolded in a very particular way. Meanwhile, out there, 4 billion hot Jupiters are being slowly stripped of their atmospheres. Neutron stars are blasting radiation onto the rocky surfaces of their pulsar worlds. Ancient gas giants orbit binary stellar remnants in globular clusters, survivors of 12 billion years of cosmic upheaval. Iron falls from the sky on worlds with no name that we will never visit. And possibly, on some cold, airless, rogue world in the dark between the stars under 100 kilometers of ice, in a pocket of liquid water warmed by the slow decay of uranium and thorium in a rocky core, chemistry is happening that we would, if we could see it, recognize. The question of whether that chemistry has crossed the threshold we call life is the most important unanswered question in the history of science, not the most important in the humanities, not the most important in philosophy or religion or any particular human tradition in science. The most important, and we do not know the answer. We have better tools than we have ever had. We have the James Webb Space Telescope staring at the atmospheres of worlds dozens of light years away, looking for chemical disequilibrium, looking for gases that shouldn't coexist unless something is producing them. We have the question more precisely formulated than it has ever been, and we still don't know. That is where we are. Not at the end of the story, not even close. Right at the moment where the instruments have gotten good enough to ask the question properly, and the universe has not yet answered. I've been waiting my whole life for this moment. Don't waste it.